Welcome! Today we're going to look at eigenvalues and eigenvectors. These are really useful in mathematics and engineering in solving ODEs, so ordinary differential equations, partial differential equations. They're useful in matrix algebra. They're useful in data science and machine learning, and much more. Let A be a square n by n matrix with real entries, much like what you see on the left of my screen. Then the eigenvalues lambda and eigenvectors x, non-zero vectors, are the scalars and vectors satisfying the eigenvalue-eigenvector equation. Ax is lambda x. So in other words, multiplication by a matrix A is the same as a scalar multiplication by lambda, when x is an eigenvector and lambda is an eigenvalue. So any vector x satisfying equation 9 is called an eigenvector of A corresponding to the eigenvalue lambda. So these come together corresponding to one another. So when you find a lambda 1, you find a corresponding x1. It's easy to show that the eigenvalues lambda 1, lambda 2 up to lambda n of A are complex numbers satisfying the determinant of A minus lambda I, where I is the identity matrix, equals 0. Since this is a polynomial of degree n, we'll have n solutions, lambda 1 through lambda n, in the set of complex numbers up to multiplicity, meaning that we might have repeated roots. And this follows from the fundamental theorem of algebra. So if we have a polynomial of degree n with complex coefficients, then we have n complex solutions. And of course, real numbers are complex numbers, so they might be real. And some of those might be repeated. So it's clear then that an n by n matrix A has at most n distinct eigenvalues. So the eigenvalue-eigenvector equation can be written as A minus lambda I times the vector x, where x is an eigenvalue. So let's put a tilde under that because I can see it's not bold, and it should be. So what we're doing here is we are just taking this over to the left-hand side of the equation. So ax minus lambda x is the 0 vector, and then we factorize out the x on the right, just like that, to give us this alternative form of the equation. So uppercase I is the n by n identity matrix, and we assume that the entries of A are real numbers. We want non-trivial solutions, and so for this to occur, A minus lambda I must be singular, so not invertible, meaning that the determinant of A minus lambda I is 0. Right, now also notice that the vector x is an element of the null space of A minus lambda I. And since this is a vector space, there are infinitely many elements of this null space. So when you choose your eigenvector, you want to choose a simple version, right? You don't want to take some large scalar multiple of the simplest version. Okay, so back to this equation. So when we expand this, we're going to get a polynomial of the following form: bn lambda to the n plus bn minus 1 lambda to the n minus 1, and so on down to the constant term b0 equals 0. All right, and so this is a polynomial of degree n, and so there are n complex solutions, so n solutions lambda in the set of complex numbers. And remember what this is the set of all a plus bi, where a and b are real numbers and I is the square root of -1. So even though the entries of A are real, you can possibly get non-real eigenvalues. So the solution gives real values lambda I or complex values that occur in complex conjugate pairs. Okay, so when you solve a polynomial equals 0, finding the roots, when the roots are not real, so of those roots that are not real, they always come in complex conjugate pairs. So in other words, if lambda is equal to a plus bi with b not equal to 0 is an eigenvalue of a, uppercase A, then so is overline lambda a minus bi is also an eigenvalue of a, because when we have non-real solutions to a polynomial equation equals 0, those non-real solutions come in complex conjugate pairs. All right, now let me see if I can just give you an example of this here. If I just pick a polynomial that I know has complex solutions, and I solve this, say, using the quadratic formula, all right, so let's give a numerical solution so you can see what they look like. So we've got minus a half plus or minus root 3 on 2i. Okay, so if I enter this plus the square root of 3 times I, where this uppercase I in this case means the square root of -1 in the software. Okay, and so let's say x minus this times, okay, so let's expand this. And you'll see it gives x squared plus x plus 1. So these are non-real roots, the two of these, and they come in complex conjugate pairs. Right, so if you were to add these together, you would get a real number, and the imaginary parts are opposites in sign of one another. Okay, let's move on to the next page. Find the eigenvalues of the matrix. Now we have a 5 by 5 matrix. And so let's take the determinant of a minus lambda I. So I'll do this on here. Okay, so there's a. Then if I subtract lambda times the 5 by 5 identity matrix, and so I'll insert that here. Okay, let's have a look. This is what we've got. And then how about we display that as a matrix? Okay, there we go. And now let's take the determinant of this. So we have a polynomial of degree 5. Okay, and now let's solve this numerically. And have a look at the solutions. Excuse me. Okay, so we have lambda 1 is minus 7.87362 and so on. Then we have another real solution, 3.87177 and 15.0574. And then we have two complex non-real solutions, but you'll see that they come in complex conjugate pairs. So we have 1.472 and so on, minus 6.001i, and then the other one is the same but with a different sign on the imaginary part. Okay, so we have these solutions right here. Lambda 4 and lambda 5 are in complex conjugate pairs. The set of all linear combinations of the eigenvectors of real valued A forms a subspace of Cn. Now Cn is a vector space over C of dimension n. Okay, example 12.2. Let A be the 2 by 2 matrix 3, 1, 2, 2. x1 is 1, minus 2, and x2 is 1, 1. Now let's have a look. Ax1, this matrix times x1. And if we expand that out, we have 3 minus 2 is 1. And we have 2 minus 4 is minus 2. So we have x1. So in other words, A times x1 gives us x1. So this says that the eigenvalue corresponding to this eigenvector x1 has to be lambda 1 equal to 1. Because matrix multiplication is coinciding with scalar multiplication here. All right, now for ax2, we have A times x2. This gives us 3 plus 1 is 4, and 2 plus 2 is 4, and that's 4 times 1, 1. So here we have lambda 2 is equal to 4, corresponding to the eigenvector 1, 1. Okay, now to find these given the matrix A, we seek the roots of the characteristic equation. Now this should say A minus lambda I, so change that in your copy. So determinant of A minus lambda I is the determinant of 3 minus lambda, 1, 2, 2 minus lambda. And so if we take the product of the diagonals and subtract the product of the off diagonals, we've got 3 minus lambda times 2 minus lambda minus 2, and when you expand that out, you've got lambda squared minus 5 lambda plus 6 minus 2 equals 0. So next we want to factorize this. So 4 is 1 times 4, and 1 plus 4 is 5. So our factorization is lambda minus 1 times lambda minus 4 equals 0. So we've got eigenvalues of A, lambda is 1 and lambda is 4. To find the eigenvectors, namely x1 corresponding to lambda 1, we use that eigenvalue in the equation A minus lambda 1I times x1 is the 0 vector. So now this should be a bold vector x1 So x1 is in the null space of A minus 1 times I. And so we take that 1, subtract it from our diagonal elements, and have a good look at the corresponding matrix. So we get 2, 1, 2, 1, and this is equivalent to 2, 1, 0, 0, subtracting row 2 from, subtracting row 1 from row 2, we've got a row of zeros. And so now we can just read off an element of the null space of this matrix just by swapping the entries, putting them in column form, and putting a minus sign on one of them. But you can check that here as well. 2, 1, 0, 0 multiplied by 1 minus 2 gives us 2 minus 2 and then 0. So we've got the 0 vector. But I just look at these, write this in the reverse order as a column, and put a minus sign on one of them. To find the eigenvector x2 corresponding to lambda 2, which is 4, we have a minus 4I times x2 is the 0 vector. So the vector x2 is an element of the null space of a minus 4I. And so a minus 4I is right here. So we simplify this. We've got minus 1, 1, 2 minus 2. We row reduce this so that we have a row of zeros. And this is just replacing row 2 with row 2 plus 2 row 1 to give us a row of zeros. And then we can simply read off that our corresponding eigenvector is 1, 1. But notice 1 minus 1, 0, 0 times 1, 1 is 1 minus 1, 0, which is the 0 vector. Okay, let's move on to the next page. If x is an eigenvector of A and k is a scalar, then kx is an eigenvector of A. Alright, so let's give a little proof of this. So we've got ax is lambda x. Now we want to multiply throughout. By k. So we have this. But since this is scalar multiplication here, that k multiplies through by every element of A, but then we can pull that out and put it over here next to the x. So this is k times x on the right hand side. And again, this is scalar multiplication, so we can move this through. And so this is what we have. And what this shows you is that kx is an eigenvector of A. Provided that x is an eigenvector of A. Okay, theorem 46. If A is a 2 by 2 matrix, then the characteristic equation is lambda squared minus the trace of A times lambda plus the determinant of A equals 0. So this just predicts, without you having to calculate the determinant of A minus lambda I in general. Okay, so here, let's write, we claim that the determinant of A minus lambda I, where I is the identity matrix, is equal to lambda squared minus the trace of A times lambda plus the determinant of A. Okay, so that's what we're doing here. So let's have a look. So we let uppercase A be equal to A, B, C, D. Since here it's 2 by 2, then the trace of A, this is defined as the sum of the diagonal elements of the matrix. So we have A plus D, and the determinant of A is A times D minus B times C. Okay, so now let's calculate the determinant of A minus lambda I. So this is the determinant of A minus lambda, B, C, D minus lambda. And so that is simply A minus lambda times D minus lambda minus B times C. And so now let's expand this out. We've got lambda squared, and we have minus A times lambda minus D times lambda, and then plus AD, and we still have minus BC. Okay, now this next to the lambda is minus, in brackets, A plus D, which was the trace, and this right here is the determinant. So this holds true. Okay, theorem 47. Let A be a square matrix. The following are logically equivalent. Lambda is an eigenvalue of A. The null space of A minus lambda I is non-trivial. The row-reduced echelon form of A minus lambda I has a row of zeros. And the determinant of A minus lambda I is 0. Okay, so 1 implies 2, since Ax minus lambda x equals 0 vector. So by definition of eigenvalue, so A minus lambda I x is the 0 vector. Hence x is an element of the null space of A minus lambda I. So it's non-trivial because there's a non-trivial element in it. Okay, now next, 2 implies 3, since the null space of A minus lambda I is not just the 0 vector, so we must have A minus lambda I with a row of zeros. Because remember, when the null space is trivial, that corresponds to the matrix being invertible. So let's write otherwise. This is invertible when null space is trivial. So we must have a row of zeros in the row reduced echelon form of A minus lambda I. Okay, now 3 implies 4, since when there is a row of zeros, the determinant of the matrix has to be 0. So the row reduced echelon form of A minus lambda I has a row of zeros, implies that the determinant of A minus lambda I is 0. And finally, this implies 1. So when the determinant of A minus lambda I is 0, that implies that lambda is an eigenvector of A. All right, and so all of these have to be logically equivalent, because what we have here is 1 implies 2, 2 implies 3, 3 implies 4, and 4 implies 1. So they're all logically equivalent. All right, so let's see some examples. Find all of the eigenvalues and eigenvectors of the matrix 5, 3, 2, 10. So let's have a look at the trace of the matrix A. We have 5 plus 10. This is the sum of the diagonal entries. This is 15. And the determinant of A is 5 times 10 minus 3 times 2, which is 50 minus 6, which is 44. Okay, and so then the characteristic equation is lambda squared minus the trace of A times lambda plus the determinant of A equals 0. So if we simplify subbing in the trace and the determinant, we've got lambda squared minus 15 lambda plus 44 equals 0. Okay, now 44 is equal to 4 times 11, and 4 plus 11 is 15. So this has an easy factorization. Let's work out the sign. They've got to be both minus inside here, so that they add up to minus 15 lambda when we expand that. So let's put lambda 1 is 4 and lambda 2 is 11. All right, now let's find x1, the eigenvalue the eigenvector corresponding to the eigenvalue 4. So to find x1 corresponding to lambda 1 equal to 4, we take A minus 4I and so this is 5 minus 4, 3, and 2, and 10 minus 4, which is 1, 3, and 2, 6. And this is equivalent, in the row reduced echelon form is 1, 3, 0, 0. Okay, so now from this, we seek an element of the null space of this matrix. So we can see that the vector 3 minus 1 is an element of the null space of a minus 4I. Since 1, 3, 0, 0 multiplied by 3 minus 1 gives us 3 minus 3 and 0, which is the 0 vector. Okay, so x1 is equal to 3 minus 1. To find x2 corresponding to lambda 2 equal to 11, we've got a minus 11I is 5 minus 11, 3, 2, 10 minus 11, which is minus 6, 3, 2, minus 1, and this has row reduced echelon form. Well, I won't give the row reduced echelon form. I'll keep it in integers because we don't have to. We just have to get the row of zeros and then read off an element of the null space of this matrix. Okay, so we see that the vector 1, 2 is an element of the null space of a minus 11I, since 2 minus 1, 0, 0 times 1, 2 gives us 2 minus 2 and 0, which is the 0 vector. So we put x2 is equal to the vector 1, 2. But any multiple of this would be fine. All right, let's move on to the next page. Find all of the eigenvalues and eigenvectors of the matrix 3, minus 4, 2, minus 6. So the trace of A is 3 minus 6, which is minus 3. Determinant of A is 3 times minus 6 minus 4 times 2, which is minus 18, plus 8, which is minus 10. Okay, so the characteristic equation is lambda squared plus 3 lambda minus 10 is 0. Now 2 times 5 is 10, and 5 minus 2 is 3, so lambda minus 2 times lambda plus 5 is 0, which gives us lambda 1 is 2, and lambda 2 is minus 5. Okay, so for x1, we have a minus lambda 1 times I equal to 3 minus 2 minus 4, 2 minus 6 minus 2, which is 1 minus 4, 2 minus 8, and the row reduced echelon form has a row of zeros. So now we can read off x1 is equal to 4, 1. Okay, now for x2, a minus lambda 2I is 3 minus 5, so that's 3 plus 5, minus 4, 2, minus 6, plus 5, which is 8, minus 4, 2, minus 1, and so we've got 2 minus 1 with a row of zeros underneath that, so we can read off x2 is 1, 2. Okay, great. So let's move on to the next page. Find all of the eigenvalues and eigenvectors of the matrix 1, 1, minus 3, minus 1. So the trace of A is 1 minus 1, which is 0. Excuse me. The determinant of A is 1 times minus 1, minus 1 times minus 3, minus 1 plus 3, which is minus 2. Okay, so the characteristic equation is lambda squared plus 0 lambda, or minus 0 lambda, minus 2 equals 0. So it's plus the determinant. Let me just double check this on the computer, because my notes say different. Okay, so this says that we should have, yeah, we have a positive determinant here, so that should be plus 2. Okay, so good. Now the roots of this, we've got lambda minus root 2I times lambda plus root 2I. When we expand this, we get lambda squared plus 2. Okay, or you could use the quadratic formula to do this. Now this says lambda equals, or lambda 1 equals plus root 2I, and lambda 2 equals minus root 2I. So these are our eigenvalues. They're complex and not real. And so now let's have a look at the corresponding eigenvectors. So for x1, a minus lambda 1I is 1 minus root 2I, then 1, then minus 3, then minus 1 minus root 2I. Okay, now when we do row reduction on this, we will get a row of zeros, even though it doesn't look like we're going to. And so now to see that, let's take the product 1 minus root 2I times 1 plus root 2I and expand this. 1 times 1 is 1. Then we have minus root 2I. Then we have the outer product, which is plus root 2I, and then minus root 2I times plus root 2I. Okay, so that gives us 1. Now the inner terms vanish, This product here gives us minus 2 I squared, but I squared is minus 1. And so we've got that product being 3. Okay, so now that we know that the product is 3, what we would do to show that that row 2 is a multiple of row 1 is we would multiply throughout by minus in brackets 1 plus root 2 times I, and we would get the second row. So we see then that A minus lambda 1I is row equivalent to 1 minus root 2I, 1 with a row of zeros. And so again we can read off an element of the null space here by swapping and putting a minus sign on one of them. Okay, so we would get 1 and then minus 1 plus root 2I. Alternatively, I think the machine would give me the bottom number being 1 or minus 1. So let's have a look here what the machine would give me for the eigenvectors of this matrix. Okay, so the machine gives me the second entry. So let's say OR, and this is just a scalar multiple of this, by the way, but it would give me minus 1 minus root 2I over 3 followed by 1. Okay, and we'll say which is a scalar multiple and remember all scalar multiples would be fine, but you tend to want to pick one without numbers that are too large in it. Alright, now for the eigenvector corresponding to lambda 2 we do the same sort of thing. Let's do that over here. We'll keep it brief. So for x2 we take a minus lambda 2I, and so that is, now for this one we used that eigenvalue, so now we're going to subtract minus root 2I, and so we have 1 plus root 2I, 1, and minus 3, minus 1 minus, sorry, minus 1 plus root 2I. We will get a row of zeros in this. And then from that we can read off the eigenvector. Put this in a box here because I'm running out of space. And there we have it. 1 minus 1 minus root 2I, or some scalar multiple of that. Okay, let's move on to the next page. So we can also do this for 3 by 3s by hand, but we can't use the trace and the determinant of the matrix A because it works somewhat differently for 3 by 3s and greater. So let's take det A minus lambda I. So this is the determinant of 1 minus lambda, 2, 1, 3, minus 1 minus lambda, 0, 1, 0, and 1 minus lambda. This is supposed to be 0. Now let's take that determinant. So we have 1 minus lambda times minus 1 minus lambda, 0, 0, 1 minus lambda, subtract 2 times the 2 by 2 determinant, 3, 0, 1, 1 minus lambda, plus 1 times the determinant, 3 minus 1 minus lambda, 1, 0. Okay, let's simplify this. So for this part, we've got 1 minus lambda minus 1 minus lambda times 1 minus lambda. Now for this part, we have minus 2 outside of 3 minus 3 lambda, subtract 0, and then plus 0 minus the product of these, which will be plus 1 plus lambda. Okay. So let's expand this now. 1 minus lambda times, now the product of these two will give us a difference of 2 squares when we pull this minus out the front. So it would give us 1 plus lambda times 1 minus lambda, which is 1 minus lambda squared, but then we put that minus back in, and we've got lambda squared minus 1. Now this product here is minus 6 plus 6 lambda, and then plus 1 plus lambda. Okay, expanding, we have minus lambda cubed plus lambda squared minus 1. Minus lambda cubed plus lambda squared. Now how many of the lambdas are there? There's 7 over here, plus 1 is 8. Then we have minus 5 minus another 1 is minus 6. Okay, and now what are the factors of this? Let's have a look. Now let's call this P of lambda. So if we sub in 3, for example, P of 3 is equal to minus 27 plus 9. 8 times 3 is 24 minus 6. So this is 33 minus 27 is 6 minus 6 is 0. And so what that tells us is that lambda minus 3 is a factor of P of lambda, which is this. We're trying to find roots of this. So we can do the rest by long division. It's a comma, okay? Minus lambda squared divided by lambda is minus lambda. Sorry, lambda cubed, right? So minus lambda squared. I take this, I multiply, I write it underneath. Take the difference. These vanish, so we have minus 2 lambda squared plus 8 lambda minus 6. minus 2 lambda squared divided by lambda is minus 2 lambda. I take this, I multiply, I write it underneath. Take a difference, we've got 2 lambda minus 6. 2 lambda divided by lambda is 2. So then we've got the product is 2 lambda minus 6. So we have a 0 remainder there. So our polynomial p of lambda is equal to lambda minus 3 times minus lambda squared minus 2 lambda plus 2. Now, can we factorize this? It looks to me that that's irreducible, at least over the integers. So let's use the quadratic formula to find the roots of this. So negative b is 2 plus or minus the square root of minus 2 squared is 4. Minus 4 times minus 1 times 2 all over 2 times minus 1. Now inside the square root we have 4 plus 8, which is 12. The square root of 12 is 2 root 3. So we have 2 plus or minus 2 root 3 all over minus 2, which gives us minus 1 plus or minus root 3. Okay, now I need to grab another piece of paper to continue this. Maybe you have more room on your page. So we've got the eigenvalues. Lambda 1 is 3. Lambda 2 is minus 1 plus root 3. And lambda 3 is minus 1 minus root 3. Okay, and then you would find the eigenvectors of the matrix A by seeking elements of the null space. Right, so let's say then seek elements of the null space of A minus lambda subscript j times I for j equal to 1, 2, and 3. So in other words, for each of these. Right, but I will just jump on the computer and tell you what those are. Okay, so let's insert a 3 by 3 matrix. So what was the matrix? We had 1, 2, 1, and we had 3, minus 1, 0, and 1, 0, 1. Okay, I'll write eigenvalues. So it confirms what we got here, 3 minus 1 plus root 3 and minus 1 minus root 3. Now let's take these. I'll subtract 3 from the diagonal here. And then I'll say row reduce. Okay, so let's write this here. we've got 1, 0, minus 2, 0, 1, minus 3 on 2, and 0, 0, 0. So remember, what I want to do is write a vector that is in the null space of this matrix using the row reduced echelon form here. So remember, I parameterize. So we've got x minus 2z equals 0. Then we've got y minus 3 over 2z equals 0. And z equals z. Okay, and so I take this and I write x is equal to 2z, y is equal to 3 over 2z, and z is equal to z. And then put 2 3/2 1 times z, and so I see that the vector, now let's just multiply this throughout by 2 because I can take any multiple of this. So 4, 3, 2 is in the null space of a minus 3I. And any multiple is fine. Okay, so this will be an eigenvector of the matrix. So let's say x1 is equal to 4, 3, 2. Okay, now I'll go and ask Mathematica for the eigenvectors of that matrix A. Okay, and so you can see 4, 3, 2 is in the list. And so the others would be, now remember, the eigenvalues gave me a different order than the ones that I found up here. So I'm going to assume that they're in a different order here as well in the eigenvectors. Okay, and these are my other two eigenvectors corresponding to lambda 2 and lambda 3. Which you can find in the same process, right? But it's somewhat painful because we've got root 3 involved. Okay, next example, 12.7. Couple the ODE, our differential equation, y double dash plus y dash plus y equals 0, and write the corresponding characteristic equation using eigenvalues. All right, so the way we do this is we let z, which is a function of x, be equal to y dash of x. So then differentiating z dash of x is equal to y double dash of x. And then let's have a look at our differential equation. So what this says then is z dash of x is equal, or sorry, plus y dash of z Okay, so we get this. Now we want to write, rearranging, solving for z dash. So we've got minus y of x minus z of x. And then we'll rewrite above that y dash of x, which is z of x. Okay, so we've got this. Now let's write this as a matrix equation First letting uppercase Y be y of x, z of x, so that uppercase Y dash of x is the vector y dash of x, z dash of x. Okay, so now what we see here in this is that uppercase y dash of x is equal to the matrix 0, 1, minus 1, minus 1 times y z, which is 0, 1, minus 1, minus 1 times uppercase y of x. Okay, so in other words, y dash is equal to some matrix A times y. Now the trace of the matrix A is minus 1, sum of the diagonal elements, and the determinant of A is 0 minus minus 1, which is plus 1. So the characteristic equation is lambda squared plus lambda plus 1 equals 0. And so the quadratic formula, and we've done this on the computer earlier, this one, quadratic formula gives us lambda equals -1 plus or minus the square root of 1 minus 4 all over 2, which is minus 1 plus or minus root 3i, where I is the square root of minus 1. And so we have eigenvalues. Lambda 1 is minus 1 plus root 3i over 2, and lambda 2 equals minus 1 minus root 3 times I all over 2. And so this also gives us a solution to the differential equation. So we see that y of x is, if you do a course in differential equations, then this is part of what you'll do. And so I would recommend that you study Math 302, because that's a course on differential equations. So we have e to the minus 1/2 x, and then we have times b1 cos of root 3 on 2x plus b2 sine of root 3 on 2x. And that's the solution to our differential equation, where what we're doing is taking the real part of this eigenvalue and placing it up here times x, and taking the imaginary part, and that's what goes inside the cos function and the sine function. Okay, let's move on to the next page, where we'll talk about diagonalization of matrices. So definition 36, a square matrix A is diagonalizable if there exists an invertible matrix P such that D is equal to P inverse times A times P is a diagonal matrix. Equivalently, A is equal to P D P inverse. And we can achieve this using eigenvalues and eigenvectors of the matrix A. Theorem 48, let an n by n matrix A is diagonalizable if and only if there are n linearly independent eigenvectors of A. If A is diagonalizable, then let x1, x2, xn be the linearly independent eigenvectors of A. Concatenate those into a matrix P, and then put D is P inverse A P, with the diagonal entries of D being the eigenvalues. Okay, and you get a diagonalization of the matrix A using the eigenvalues and eigenvectors of the matrix A. Let's have a look at example 12.8. Diagonalize the matrix A, 5, 3, 2, 10. Now we've already done this, I believe, but let's just use a computer, or you can look up what you got earlier. So 5, 3, 2, and 10. Okay, so we got eigenvalues. I think we had these with order lambda 1 is 4 and lambda 2 is 11, if I remember right. And so then x1 was let's see, what did we choose? We chose well, we would get 1, 3 up here, so we would have then 3 minus 1 is what we would have chosen for x1. And then when we put in lambda 2 into a minus lambda I, we would have minus 6, 3. And then in the bottom row, we would have 2 minus 1. So we would have chosen eigenvector 1, 2 for x2. Okay, so now that we've got our eigenvalues and eigenvectors, what would the diagonalization look like here? Well, we would write A equals 3 minus 1, 1, 2 times the diagonal matrix 4, 0, 0, 11, and then times the inverse of this matrix P. Now the inverse, we can do this in our head. The determinant of the matrix P is 7, so we would have 1/7. Then we swap our diagonal elements, put minus signs on the off diagonal elements, and there's our inverse. Okay, so now let's try this out on the computer. So 3, 1, minus 1, 2. So this is our matrix P. And then we claim that the diagonal matrix is 4, 0, 0, 11. And then we take this, swap diagonal elements, put minus signs on the off diagonal elements, and then there will be a 1/7 in front of that, but we can do that last. So let's just take this product and then divide the result by 7. Okay. And so we get 5, 3, 2, 10, which is the matrix A. So yes, this works, and this is our diagonalization of that matrix A using eigenvalues and eigenvectors. Okay, I need to include a couple more pages here because, or actually, you know what? We can write this in under the definition. There's a bit of space here. So let's say when, because this is the application of this diagonalization, or at least one of the applications of this. So when we have A equal to P D P inverse, then A to the power of, say, M is equal to PD P inverse times PD P inverse, and so on, times PD P inverse. So m of these. So m times. Now notice P inverse times P will give you the identity matrix. So what we'll end up with is loads of these giving you the identity matrix. And we would end up with d to the power of m. So P d to the power of m P inverse. And so this gives you an easy way to take the mth power of a matrix because of this nice property that P inverse times P is the identity matrix. And so the mth power of a diagonal matrix is really easy. So let's say note lambda 1, lambda 2, etc. lambda n to the power of m is lambda 1 to the power of m. Then the second one would be lambda 2 to the power of m, etc. down to lambda n to the power of m. So it's really easy to take the mth power of a diagonal matrix just by taking the mth power of those diagonal elements. Okay, let's move on to singular value decomposition. A generalization of diagonalization is called singular value decomposition, or SVD for short. This is a decomposition of a not necessarily a square matrix A of dimension m by n into the matrices U, S, V transpose, where U is an m by m orthogonal matrix, V is an n by n orthogonal matrix, and S is an m by n diagonal matrix. Note that since S is not necessarily square, it's not a proper diagonal matrix. All of its non-zero values must lie on the main diagonal. These values are called singular values of A. If there exists a number sigma and vectors lowercase u and v such that A v is sigma u, A transpose u is sigma v, then sigma is a singular value of A with corresponding left and right singular vectors u and v. We can also calculate the singular value decomposition using diagonalization. So notice that A transpose A would be, and now what I'm doing here is, so note that the transpose of a product, so AB all transpose, is B transpose A transpose. All right, and so if I take this and transpose this, so the transpose of US V transpose is equal to V transpose transpose S transpose U transpose. V transpose transpose is V. So we have V S transpose U transpose. And so this in here is the transpose of A, where A is U S V transpose. Okay, now since U is orthogonal, U transpose times U is the identity matrix. So let's write that here in the margin. Since U is orthogonal, we have U transpose times U is the identity matrix. And so then that becomes V S transpose S times V transpose. Okay, on the other hand, A times A transpose is US V transpose times V S transpose U transpose. And again, since V is orthogonal, this on the inside here, V transpose V, is the identity matrix. Let's note that in the margin. Okay, and so we have U, S, S transpose, U transpose. Now, since S is diagonal, so is S transpose S and S, S transpose. And so SS transpose is diagonal. Likewise, S transpose S is diagonal. Okay, and so what this means is that we can calculate the singular value decomposition by taking eigenvalues and eigenvectors of A transpose A and AA transpose. So we diagonalize the two symmetric matrices. The right singular vectors of A are the eigenvectors of A transpose A, and the left singular values are the eigenvectors of AA transpose. Furthermore, the singular values of A are the square roots of the eigenvalues of A transpose A and AA transpose, which coincide. They are identical. Okay, so now in closing, what I want to do, and there's some blank space here, so let's just do this. Let me find, okay, since we've got a diagonalization already, so 5, 3, 2, 10 is our matrix A, for example, and we found that we could express this, decomposing this into this product and so I can easily take, say, the 10th power of A and so that will be this times 4 to the power of 10, 0, 0, 11 to the power of 10. Right, which would be easier because there are only 3 matrix multiplication, or 3 matrices being multiplied here, so 2 matrix multiplications rather than 9 matrix multiplications. So let's note that. So this is 2 matrix products rather than 10 minus 1 equals 9 matrix products. So you see it can be easier to diagonalize and then take the matrix product than to actually multiply this out. Okay,